Good evening, everyone. Mr. Dolowitz here for college trigonometry. So I'm going to try recording the video this week using YouTube Recorder versus the online Blackboard because there seems to be some issues with capturing the video. So while that's getting worked out, and it could be very well on my part, but while I figure that out, I definitely want you to have access to the recording. So I'm going to use YouTube this week. And well, with no further ado, please check your emails. So most importantly is that you submit your attendance for the week. I need to have that by tonight, 11:59 midnight. So I will submit that when I wake up in the morning. Secondly, you'll find these PDFs that I'll be working through in the next few videos. And as I said, or as I'm about to say in the Blackboard message, you'll work at these right now and kind of check in with me with questions along the way. So with no further ado, I'm going to switch over to what you received in your email from section 3.1, which is titled Basic Identities. And I've typed this up myself. I'm not actually using the PowerPoint slides. So can follow along as I read this. An equation can be true or false. All right, bottom line. So if we consider a simple equation like 2x minus 1 is x, that's only true when x is 1. You could easily prove that by basic algebra. Subtract x on both sides, adding 1 on both sides. I can almost visually see subtracting x on both sides and adding 1, x is 1. Meaning, right, so if you look at the left-hand side there and you just substitute in 1, 2 times 1 is 2, take away 1 is 1. On the right-hand side, substitute in 1, that's it. So you'd have the left side equal to being 1, the right side equals 1, obviously 1 equals 1. If you substituted in any other number like 0, the left-hand side would make -1, the right-hand side would make 0. Clearly, -1 is not equal to 0. And so algebra allows us to show that the only solution is when x is 1. Otherwise, it's false. However, any equation that's true for every single value in its domain, we say, but in easy terms, if you can plug in almost infinite number of numbers into an equation and the left side is always equal to the right side, if it's always true, not just like at selected values, we call it an identity. And you've had some exposures with identities. So for instance, 2x plus 6 is equal to 2 times the quantity x plus 3. In section 3.2, we prove identities, but given the restraints of this semester, we are going to hold off on that. If there's time at the end of the semester, we'll look at that. But yeah, we can just basically say 2x plus 6 is definitely always true by the distributive property or by factoring, no matter what you plug in on the left. So for instance, let's choose an easy number like 0. 2 times 0 is 0 plus 6 is 6. Substitute in 0 on the right, you make 6. Choose another number like anything you want, 10. On the left, you'd get 26. On the right, 13 times 2 is 26, right? Obviously, so no matter what you substituted in, the two sides will always be equal. Therefore, it's called an identity. So I'm going to switch over now strictly to the document so I can use my tablet mode here to write, and then I'll kind of interchange. And at this point, you should be either printing this out or following along and copy it into your notes. So we're going to construct some identities using some algebra concepts, basically just expanding and foiling, or however you want to describe it. So we can make an identity by applying algebra to expressions. Sorry, just getting this set up here. No, I don't want to take any pictures. And so basically, all I'm going to do here is expand. Wow. Two cosine beta times cosine beta would be 2 cosine squared beta. This term we would get minus 2 cosine beta. Distributing the 1 cosine beta, and our last term, a -1. Combining like terms in the middle there, 2 cosine squared beta minus cosine beta minus 1. There's our first identity. So basically just, again, using your ideas and concepts from algebra to expand expressions containing trig functions to create identities, right? We can also undo expanding by factoring. So just want to remind you, you can split the middle when you have 3 terms, which requires us to find the product of 2 and -3, which is -6. Find factor pairs of -6, whose sum is 1. And we found it, or I found it, 3 and -2. So we literally split the middle into 3 cotangents and -2 cotangents. So this is equal to 2 cotang, oops. So there's our split the middle step, and reminding us once you have 4 terms, you want to look and factor by grouping, factor out the greatest common factor in your first 2 terms, factor out the greatest common factor of your second 2 terms. So this is equal to cotangent alpha of 2 cotan alpha minus 3. Factor out the 1. You have, what am I missing here? Oh, this should be a 2, right? My bad. Copy that wrong. So please make sure you get that back. Would have been nervous there. 2 cotangent alpha minus 3. I see I got my common group. And there we go. There's your identity by factoring. So you can create an yeah, hopefully I didn't lose you there. I'm not sure what happened, but back at it here. Sorry, still getting this down packed. So basically use your rules of algebra to either expand expressions or factor expressions to create identities. But we're going to move on now, and at this point, I'm going to ask you to refer to those pages in your book. If you don't have the book with you for whatever reason, you log into MATLAB, and the e-text is available there. What's nice is you can just type in the page number at the top and it brings you right there. So these are common trigonometric identities, right, that you need to be familiar with. Please enter them into your notebook. Commit them to your long-term knowledge if you are going into any type of mathematics, science, STEM field. Okay. So if you're taking pre-calculus and beyond, you need to know these identities very, very well, right? Having taught calculus many times, the difference between students who have success in calculus versus those who struggle are the ones who take the time and know their trig identities and know their trigonometry, all right? So please, again, copy these down and commit them to long-term knowledge, your long-term memory. They are called the reciprocal identities, the tangent and cotangent identities in terms of sine and cosine on page 166, the Pythagorean identities, and even-odd identities. So I would ask you to pause the video at this time to look at those, read those over, copy them into your notebooks. And once you are done with that, return to this video. Now that you have copied those into your notebook, identities are used in many ideas and concepts in calculus. One of the most common is to simplify or rewrite advanced expressions in simpler ways. So one strategy for simplifying is to write all trig functions in terms of sine or cosine, and that's stated in the book on page 168. So we're going to look at now simplifying these next few expressions using the identities, and I've scaffolded them. I've written them in a way that we start with just writing sines and cosines and then applying the other identities that you copied into your notebooks as well. So we can immediately apply the reciprocal identity for cotangent as cosine of x over sine of x. And then the cosecant is the reciprocal of sine. So we can write this as 1 over sine x. All right. Now, when our fractions are written like this, it might be a little bit neater to stack them kind of in a more traditional manner and write the quotient of two fractions literally as the division symbol. And then using some basic arithmetic rules, that division is the same as multiplying by a reciprocal. And we have some simplifying there. This expression simplifies cosine of x. So you can see where originally we had a quotient of two trig functions, both of them being reciprocal trig functions, through some basic arithmetic rules and basic trigonometric identities. This can instantly be rewritten as cosine, and that'll be helpful in future coursework. We're going to add two trigonometric fractions. So we'll follow the instructions to first write these in terms of sine and cosine. So this is 1 over sine and cosine. This is 1 over cosine. So I'm kind of curious what's going on here. So I'm going to look at this first fraction. Right? I'm just going to work this and say this is sine x divided by 1 over sine x. Over here we have cosine x divided by 1 over cosine x. Let me clean that up a little bit. And similar reasoning, we can multiply by the reciprocal, and this group would turn to sine squared x, and this group would become cosine squared x. And you might say, well, those aren't like terms. I'm done. Well, I ask you now to refer to your Pythagorean identities, which say that sine squared of an angle plus cosine squared of that same angle makes 1, which if we can condense these two trig functions to the number 1, definitely simpler. So by the Pythagorean identity, this expression simplifies to 1, right? Pretty neat. That fraction, original fraction in calculus, could be rewritten as 1. But I'll stop with the calculus references. You'll get there when you get there. But for now, your goal is to be able to manipulate these expressions using trig identities and simplifying. All right, so now we're going to do multiple skills or multiple identities. So I'm still going to follow the instructions to rewrite everything in terms of sine and cosine, and then we can proceed. So by the reciprocal property, cotangent is cosine divided by sine. And we also have this sine beta. All right. So immediately I can simplify, and I notice that I now have two binomials which make a difference of squares. And again, you might argue that this expression is simplified, but one strategy I would tell anyone is whenever you're taking or simplifying trigonometric expressions and they involve a square, meaning a sine squared, a cosine squared, a tangent squared, a secant squared, anytime you have a trig function containing something to the second power or beyond, but definitely second power is the biggest clue, you want to refer back to your Pythagorean identities. And looking at those now, there is a Pythagorean identity that relates cosine squared and sine squared. And we mentioned it just a moment ago, that the cosine squared plus the sine squared, which I said in reverse order, but equals 1. Well, if we do some basic manipulation here and subtract cosine squared on both sides, you have an identity that states sine squared of an angle is 1 minus cosine squared. And we have that, right? This is right there. So this is very common practice. Again, anytime you have a trig function squared, and here's another hint, that and the expression also contains a 1, you definitely want to check your trig Pythagorean identities to see if you can simplify. So the argument is, since we have two terms, 1 and negative cosine squared b, it's just easy to call this sine squared beta. So this is pretty common practice. Again, I just want to remind you that your biggest clue to do this is that you have a trig function being squared and that it contains the value of 1 in it. All right. Now, I'm going to tweak the directions a little bit. I could absolutely go through and do this by rewriting everything in terms of sine and cosine, and I encourage you to try it after I do it or before I do it. But you can also just use basic rules of arithmetic as long as they're legal, right? As follows. So here's just an alternative to rewriting everything in terms of sine and cosine from the beginning. I'm just going to call this tangent squared x over tangent squared x minus secant squared x over tangent squared x. What allowed me to do that? Yeah, if you've thought about this, right here, this is 1, which I rewrote right here as tan squared x over itself, because that is definitely an identity from numbers, right? Anything divided by itself, as long as it's not 0, is 1. So I'm going to rewrite, as I did, 1 as that fraction. And why would I be so inclined to do that? Because I think I can now combine these, since they have a common denominator of tangent squared, as tangent squared x minus secant squared x. Now, my hint from earlier was anytime we have tangent squareds or any type of square, we want to refer back to our Pythagorean identities. And one of them that you have in your notes is that tangent squared x plus 1 equals secant squared x. So I'm going to make the substitution that secant squared is exactly tangent squared x plus 1. And through some algebra, the numerator would become -1. The denominator stays tangent squared x. And using a reciprocal identity, 1 over tangent squared is called the cotangent squared. And the negative sign carries along there. So even though the book states to write everything in terms of sine and cosine, what I've just exemplified there is that you can apply any legal moves from arithmetic, from algebra, from any other coursework. You don't necessarily have to rewrite everything in terms of sine and cosine if you kind of see something that might make your life easier along the way. But again, I challenge you to, or encourage you to, redo the same problem by rewriting things in terms of sine and cosine and see how you would proceed from there. I guess this is the last opportunity that I want to emphasize that anytime you have a tangent, any type of trig function squared that contains a 1 or a -1, definitely refer to your trig Pythagorean identities to see if you can make a substitution. We've also, well, I also asked you to copy down the even odd identities, so the next few examples will use those. So by the even odd identities, the sine of -x is equal to negative sine x. And the cotangent of -x is also equal to the negative cotangent of x. We call both the sine and cotangent odd functions. We talked about odd functions when we began our semester. I immediately noticed that a negative times a negative becomes a positive, and that I can rewrite cotangent as cosine divided by sine. And we can simplify those factors. And this entire expression becomes the cosine of x. Okay, so there's our first example using the even and odd identities. Again, we'll apply them. So a tangent is, the tangent function is odd, which means this negative sign, this negative angle of rotation can be rewritten as negative tan alpha. The cosecant is also an odd function. And we have a perfectly good cosine of alpha. I immediately again notice that a negative times a negative makes a positive, and that a positive times a positive remains positive. So my answer here is going to be positive. I will now take the strategy of writing everything in terms of sine and cosine. Tangent is sine over cosine. And we have this nice little cancellation. And so sine over cosine, it's simpler just to go back and call it one trig function whenever possible. So it turned out that this almost was a wasted step, but I didn't know that till I did it. Okay. So as you're working these, anytime you have a negative angle of rotation inside, you want to consider whether it's an odd or an even functions. If it is odd, you can informally think of that negative sign coming out front. That's not mathematically justified, but that's what that's what an odd function means. So you can almost take out that negative sign, put it in front. If it's even, and the only two even trig functions are the cosine and secant functions, you just are allowed to drop the negative sign. Right? So where are we now? Moving right along. Back to our sheet. Just emphasizing again what I just went over, that an even function is any type of function that has the property f of negative x equals f of x, and an odd function is any function such that f of negative x equals negative f of x. All right, we again talked about that earlier this semester, and I encourage you to look back in your notes there. We're going to do a test in trigonometric functions to determine whether a function is odd, even, or neither. And recalling that the test just requires us to input negative x and simplify. So we'll input negative x, meaning just replace every x with negative x. Simplify each expression. So this would become negative sine x, and cosine's an even function, so that just turns to cosine x, and this makes negative 2 sine x cosine x, which is the opposite of f of x. Right? So if you threw a negative sign here, you would put a negative sign there, and that's exactly what we're looking at. So therefore, f of x is odd. Same test, just input the opposite of the input. Tangent is an odd function. Okay. And looking at what we have, we cannot simplify this any further. Thinking out loud, if I were to rewrite this in terms of sine and cosine, that is definitely legal. Where would I go from there? I might try combining it with the 2, but I'm not going to end up with any trig function to a second power. Okay, and I'm not going to be able to combine any like terms. I think things are going to get more intense, worse off, in other words. So this is simplified. And now when I look at the expression, I have a positive 2 in f right here. This is positive 2. So far they're identical, but the sign in between them is not the same, and we can't make it the same any legal way, not that we want to. So basically, this is neither odd